All right, I know we've talked about this before, where we've had a shortcut for our organic molecules, knowing whether it's oxidation or reduction. So let's review that. Oxidation, we're adding oxygen and or removing hydrogens. Reduction is removing hydrogen and or adding hydrogens. One thing I want to point out is that the ultimate electron acceptor is oxygen. So what do you predict about its standard reduction potential when oxygen is reduced to water? Is it going to be higher or lower than everything else in the electron transport chain? If it's yes, it's going to be higher because it's accepting electrons. Gaining electrons is reduction. If it is the ultimate electron acceptor, it accepts it after everything else has given it off. So we're going to go from lower to higher. Right? When we pass from one bucket to another, we're going to pass from lower standard reduction potentials up the chain to higher ones. So in our course, we are basically looking at our redox reactions, which I think in biochemistry are the most important reactions. Our redox reactions in two ways. One, when we're just the shortcut when we're looking at just organic compounds, and we're going to use this definition. Another way is using the standard reduction potentials to predict what's going to happen or to see what's happening. All right, so now let's turn back. Oh, let's take a look at this. So pyruvate, before we turn back, is reduced because let's take a look what's happening. Pyruvate is reduced to lactate because it is gaining hydrogens, and NAD is being oxidized. NAD is supplying the hydrogen, or at least one of them. So NAD is being oxidized. NADH is being oxidized to NAD. So it is the opposite for agent, so it's a reducing agent. It's causing NADH, is causing pyruvate to be reduced to lactate. So again, this is easier to see, I think, but we don't necessarily only have organic compounds in our electron transport chain. We have a lot of metals that we use as cofactors. These are coenzymes. We can track the hydrogens on our coenzymes. But for our cofactors, our metals, we're going to have to track oxidation number. So we're going to turn back to the electron transport chain. Remember, we're going to look at the free energy. We're going to look at the through the cell potential to predict where they're going. As I mentioned before, when scientists were studying the electron transport chain, they took the complex out, isolated it, and determined what components were in it, and then figured out or postulated, hypothesized where the electrons were going, from what to what, based on the standard reduction potential. So they looked it up or determined it for each of the things they identified in each complex, and then said, hey, I bet it's gone from this thing to this thing to this thing to this thing. They did other experiments to confirm what they thought, and we'll talk about that. But we're going to note that we're going to take those things from a lower standard reduction potential, more negative, smaller number, and we're going to hand the electrons to a more higher value. And this is our table. And I believe I will give you this table or the equivalent on your exam. If you need it. So we can see that we have these values here. Here's the half reaction. They're all written as reductions because it's a standard reduction potential. That's a convention. That's how we do it. And those things with negative or smaller values will be reduced, will be oxidized, and things that have a higher value will be reduced. So here, let's take a look at NAD. There's a lot of things in here. NAD to NADH, FAD to FADH2. So these are what we're handing into our electron transport chain, right? And then we're going to give it to coenzyme Q, right? Remember I said the complex 1 and complex 2 start with FADH2 and NADH, and it's going to hand it off to coenzyme Q. Right? So it's handing it off because we're starting out with a lower number, and it's almost like pretend you're climbing a ladder. The electrons are climbing this ladder from a more negative value to a higher value. So here we're handing it off from FADH2 and NADH to coenzyme Q. And then didn't I say that we're then going to go give it to like that cytochrome C, right? That's between complex 3 and complex 4. Cytochrome C carries the electrons there. And then what is the ultimate electron acceptor? Oxygen. So it has the highest one. Pretty cool. Isn't that really neat? We're using this predict. Now, so here we have a coenzyme, FADH2, NADH. But then look at these. Cytochrome B, L, BH, C1A. They all contain iron. Iron's being reduced in these standard reduction potentials. Here we have just iron. If iron was by itself, the standard reduction potential was 0.771. What's happening in the active site of these proteins is that the iron is still being reduced, but it has a different and much lower standard reduction potential. Why do you think? It's still iron being reduced, but the fact that it's inside this protein gives it a different standard reduction potential. Does anybody else think that that's weird? It's iron being reduced. That's what the redox reaction or the reduction reaction is. And all of these things have iron. So why would this iron being reduced be different than this iron that's by itself? All about chemical environment. Those of you that have taken organic chemistry know how chemical environment can change the nature of a substance, change the nature of how something will give up a proton, accept a proton, how it can really affect the nature of a functional group. So here, this iron is not going to be reduced as easily as a cytochrome A iron. It changes it just a little bit, the tendency of this iron. So the chemical environment in cytochrome C1 is such that it causes this iron to want to hold on to the electrons a little bit more than the iron in this environment, than the iron in this environment, than the iron in this environment. So we're still using the chemistry of reducing the iron, but the environment around that causes, and we'll see, it goes cytochrome C1 to cytochrome C to cytochrome A to cytochrome A3. It's climbing this ladder in our electron transport chain. But the reaction is the same, reducing iron. But the chemical environment, the amino acids around this iron, causes it to want to give up the electrons a little bit less than the iron up here. That evolved. Let's just take a moment just to go, wow. That someone didn't think of this. If they thought of this, that would be wicked smart, right? But they didn't think of this. It evolved. It evolved so that we could have this stepwise release of free energy, right? The electrons are, the more buckets that it's not like a bucket brigade for a fire, right? We don't want to have 1 billion people in the bucket brigade because it would take forever to get the water to the fire. But here, you want as many buckets as you can because every time an electron is passed, it's a release of free energy. Sometimes it's enough free energy to push protons from the matrix to the inner membrane space. Sometimes it's not. But we want to have the more opportunities. So we have evolved these different cytochromes, these different environments around these elements that, thank goodness, they have multiple oxidation states, that they can be oxidized and reduced easily. So not only do we use iron, we use copper. Is that in here? Is my copper in here? Yeah, I don't see it. Do I see it? My eyes. All right, no, I don't see it here, but it is in here. This is just an example, though. So we're going to start down here and climb the ladder, and this is a really important concept, that the environment around that cytochrome causes the standard reduction potential to be different, that amino acid sequence around. So again, you want to flow electrons from more negative to a more positive. These have up here a higher affinity for electrons. They're a good oxidizing agent. They get reduced easily. These have lower affinity with electrons. They want to release the electrons. Really, that's what I want you to remember. More negative, more positive. And that's the flow of our electrons. So our standard reduction potentials are going to provide a basis for our comparison. We're going to use that to predict what's going to happen with a grain of salt. So, and I've said this like a billion times, we're going to predict what's going to happen. So here is, what time is it? 9:38. Okay, we'll talk about this, but we'll start up here on Monday. These, again, are another look at our complexes. So here, this green is our complex 1, this is our complex 2, this is our complex 3, and this is our complex 4. I want to introduce what's happening in these reactions. It looks a little weird. What is happening is NAD is reacting with this coenzyme FMN on this enzyme. So FMN is and we're going to take a look at it, what FMN is, but it's going to react with it. So you can see NAD plus enzyme FMN produces NAD plus and the FMN with the 2 hydrogens on it. So that's how you're going to read these. So here we have the reduced form reacting with the oxidized form to produce the reduced form and the oxidized form. Now we're going to go back. The FMN with the electrons is going to react with what we call an iron-sulfur center. This is so cool. I can't wait to talk about those. That is in the oxidized form. Then the electrons are going to be passed on to produce this FMN in the oxidized form again, and then the iron-sulfur center in the reduced form. That iron-sulfur center is then going to react with coenzyme Q to produce the reduced form of coenzyme Q, which is then going to go on to the iron-sulfur centers in complex 3. So overall, a reduced species is going to react with an oxidized species to produce the oxidized species and the reduced species. So this is reduced right here, NADH, because it has a hydrogen, that's reduced. This FMN doesn't have the hydrogen, so that's oxidized. So you can say red ox forms, reduced form, oxidized form. This is the reduced form, this is the oxidized form. Let me say that again. This, with the hydrogen, whenever you have the hydrogen there, that's reduced form. Here, NAD, that's the oxidized form. So this is getting oxidized while this is getting reduced. Remember, they happen together. So the NADH is giving up its electrons to FMN. Now this reduced form, and if it says ox, that's the oxidized form. We just we're not passing along the hydrogens. And that produces that. Now, before I go too far, forget this Q cycle. We're not studying that. So just exit out. This is the slide that I want you to study from for the exam. What is being passed to what? There's more to the story in other slides. There's differing accounts. However, I find that this slide provides the easiest way to study for the exam. Okay. Note that FADH2 is coming in from the succinate to fumarate reaction. So FAD is coming from complex 2. That gives electrons to the iron sulfur center, again to coenzyme Q in that reduced form. That coenzyme Q is going to travel through the inner membrane and then hand it off to complex 3. That has more iron sulfur centers that are a little bit different than these iron sulfur centers to give it to cytochrome C1. Then it's going to give it off to cytochrome C plain, then to cytochrome A, then to a copper ion. Note that iron, Fe, has iron 3 and iron 2 as its possible oxidation states. But copper, which is present in complex 4, has copper 1 and copper 2. You need to know that. Gives it to a different cytochrome A, and then gives the electrons to oxygen to produce water. I hope you are excited to learn more about this as I am, and we'll start that